Hi there, Rachel Chase here, and in this video we will explore hypothesis testing and its application in the real world. Hypothesis testing can be used for a variety of reasons. Specifically, we can use it to test for problems or even to verify consistency, depending on what it is that we're trying to investigate. Something to be mindful of with hypothesis testing is that although we can use it to test for a problem, it's really just to see if a problem exists. Hypothesis testing does not actually diagnose how severe a problem might be. Now, when we say a problem, this could be something as simple as in manufacturing, if perhaps a bottle is supposed to be filled to 12 ounces and you find that their bottles have been underfilled. So something like that, you would potentially lose customers if you're trying to sell them product that is underfilled from what you claim it to be. So hence verifying consistency. A little bit of notation that we need for hypothesis testing, first off, is our null hypothesis, and this is usually referred to as the original claim, because that's what should be true depending on the situation. And we denote this with an H subscript 0. We read that as H naught. And our alternative hypothesis is what we might believe is true, or in other words, what we're testing our sample of. And this we denote with an H1 for alternative hypothesis. The last two pieces of notation that we're going to need here are p-values. P-value is the area in the tail of the test statistic. So while this might not make much sense now, as we work through an example, this will become a little more clear. And if you recall from Chapter 7, when we talked about confidence intervals and estimates, a critical value is basically your significance level. So if you recall, we used alpha to denote significance level. Same thing from the previous chapter. And something with critical values are, you want to think of these as a point of no return, if you will. It's the cutoff amount of what is acceptable. To teach you hypothesis testing, we're going to split this up into 3 different categories, similar to the categories that we divided our confidence intervals into. Now, we're going to look at cases where sigma is known, sigma is unknown, and then proportions. A few things we also need are what are our hypothesis options. Now you have to keep in mind that although this is kind of the 3 main cases, these are not the only things that could technically happen in the real world. But if you understand how the concept works, you should be able to apply this to any situation. We have 2 main varieties, one-tailed tests and two-tailed tests. Every time you write out hypotheses, they are always found as a pair. So you always have H0 and H1. If you do not have this information, then whatever it is you provided is not a hypothesis test. This is the main requirement. Now, let's say you're testing to see if that bottle of soda does in fact have 12 ounces in it. So if the bottle says 12 ounces, that means that your mean should be 12 ounces. And your alternative could be one of 2 things. If you are underfilling the bottle, that means that there are less than 12 ounces, or you could potentially be overfilling the bottle. So what would your hypothesis pair be there? If the mean is supposed to be 12 ounces and it was overfilled, that means that mu is actually greater than 12. Now, while these cases both show you what could happen or what kind of test setup you would have when you're either over or underfilling, if instead you were curious to perhaps just test consistency. So for example, let's say you want to make sure that that plant is actually filling these bottles always to 12 ounces. So for example, you're not necessarily looking to see if it's underfilling or overfilling them, because in the real world, if you're overfilling the bottles, you're giving away free merchandise, and that means that you're going to lose money. On the other hand, if you underfill the bottles, you're going to upset your customers, and that doesn't work out well either. You might lose money in that regard. So why would it pay to check as you go. In other words, if you do a test, and we call this two-tailed, when you have the mean equal to that amount and the mean not equal to that amount, it means that you're verifying consistency. So this is kind of your, has there been a change? Are we verifying that nothing has changed? Is there a difference? These are all indicators. And you'll notice that none of these are directional. Whereas over here, you might say, okay, do we have evidence supporting that we're actually underfilling the bottles? Do we have evidence that we're overfilling the bottles? So each of these has some type of context that goes with it. As far as making rejection decisions, these are most easily understood once we actually get to the problems themselves, because a lot of this is very visual. Now, all of what we do is based off of the normal curve, and we're going to have to do two comparisons. We can compare our test statistic, which will be either a Z or T score, which we learned about in the last chapter, and you want to compare that to your critical value. Now, the catch here is you always look at these in absolute value. The reason for that, and you'll see this in the picture when we get there, is you're basing it off of the distance away from the mean. In other words, what is the probability? How unlikely is it to occur? If your test statistic in absolute value is greater than your critical value, we reject our null hypothesis. It means you have plenty of evidence. If it's the other way around and your test statistic is actually smaller than your critical value, again in absolute value here, then we say that we fail to reject our null hypothesis. And this is two-part here. You'll notice that we always use the phrase reject or fail to reject. You never, ever use the phrase accept, because if there is not enough evidence supporting your claim, that doesn't necessarily mean there isn't a problem. So you can never say anything other than fail to reject. This is not a reject or accept situation. Secondly here, it's always in reference to your null hypothesis. You'll notice that both of these have H naught at the end, and that's because you are making the decision about the original claim based off of what the probability of your sample actually occurring is. So while this might seem a little strange now, stay tuned, because as we work through examples, this will become a little more clear. So let's go ahead and dive into our first case, and that is sigma known. For a hypothesis test with sigma known, you've actually seen the formula for your critical value before. Your test statistic before. Your z-test score is equal to x bar minus mu over sigma over square root of n, which if you recall back, we learned about this in reference to the central limit theorem. Now we're basing our sample and how likely that sample is to occur. The hypothesis test is a multi-step process. Anytime you perform a hypothesis test, there's a few requirements. What we're going to do first is go through this problem, take a moment and read through it, and then pull out the important information. An insurance company is reviewing its current policy rates. When they originally set the rates, they believed the average claim amount was $1,800. They're concerned that the true mean is actually higher than this because it could potentially lose them a lot of money. They randomly select 40 claims for review and calculate a sample mean of $1,950. Assuming that the standard deviation of claims is known to be $500 at a significance level of 0.05, should the company be concerned? So right there, they said the standard deviation is known. So that means that sigma is equal to $500. They've specified. They said the original amount was $1,800. So that means normally, that's our population mean. That's what our payout should be. In our sample of 40, we found a mean of 1,950. At a significance level of 0.05, so alpha equals 0.05, should the company be concerned? So this is the part, that last sentence there, is what they're asking us to test. Well, let's set up our null and alternative hypotheses. They're telling us that the mean used to be or should be $1,800. Now, as a company, what would be a concern to us? If we were actually paying out less money than $1,800, it means our profit would be greater. So that's not really a concern. What would be a concern, however, is if we're paying out more money, because that means it's cutting into our profit, or potentially it could even be more than just cutting into the profit. It could be detrimental to the business staying afloat. So if we have a concern that it's greater than, that indicates a direction, right? You have to ask yourself in context what's important here. So once you have your null and alternative hypotheses set up, take a moment and sketch your normal curve. The mean of 1800 is in the center, and we call this a one-tailed test. Greater than means it's on the right side. Greater than is on the right, less than is on the left. Two-tailed is split amongst both of them. If alpha is the area in the tail, and this is only one-tailed, that means that this region is an area of 0.05. Now, what are you doing a comparison to here? We have to find a critical value, and we have to find our test statistic. The critical value is based off of the area in the tail region. So your critical value and your alpha go hand in hand. So critical value, alpha. Now, regardless of which way you like to do it, if you want to, you can use your z-score table. So if you're looking for an area of 0.05, keep in mind that if this is 0.05, the left is 0.95. So if I go into my table here, I'm going to find the closest thing I can to 0.95. Which looks like it's between 1.64 and 1.65. So that means that our our critical amount would be a z-score of 1.645. If you prefer, you can use your graphing calculator to get that number as well. You could do that using your inverse norm function. The area to the left is 0.95, and then your standard 0 and 1 when you're looking up z-scores. And you'll see that we get the same thing, our critical value of 1.645. Now, for the test statistics, so we've got our hypotheses, we have our picture, we have our critical value. For the test statistic, go ahead and plug into the formula. Z-test equals x bar is 1950 minus mu of 1800 divided by 500 over the square root of 40. When you're typing this in, if you do it all at once, just be careful that you do in fact have parentheses where appropriate. So around your numerator and then around your denominator. So this right here gives us our z-test statistic. So if you recall, all of this is dealing with a number line, right? Now, what does it mean for us to make a decision here? If you remember the decision rules, we said that when your test statistic is greater than the critical value, you may reject your null hypothesis. When it's less than, you have to fail to reject your null hypothesis. If we look at this case, we have a z-test statistic of 1.897, which if you compare those, the absolute value of a positive number doesn't change anything. That is greater than 1.645, which means that we would reject our null hypothesis. Now visually what's happening, if you look at this on a number line, remember it's 0 in the center, and to the right is positive, to the left is negative. 1.897 lands further than the critical value. So this piece where alpha is, we call that the rejection region. There's really a bunch of different names for all the same things. Whether you like looking at this as an inequality, the picture, or you want to call this the rejection region, basically anytime it lands in that tail region, it means that you reject your null hypothesis. Another option you have for calculating these hypothesis tests, once you have your hypothesis set up and your picture, you can also use under your stat menu, if you go over to tests, we have the option for a z-test, which is the first one on the list. So I'm going to enter my data. Mu is 1800, sigma is 500, and our sample mean was 1950. In this case, n equals to 40. If you want to use the z-test method or whatever test function in the calculator, this symbol down here has to match your alternative hypothesis. So we are testing that it is greater than the mean. So when we calculate, you'll see it gives us a readout. And again, this is up to you if you want to use it. The nice thing about this is that readout does provide you with your z-score. So if you're a little bit nervous typing in with the parentheses, you can even use this just to get your z-test statistic. So again, this z-score is your z-test statistic, and they round to the same thing if you did have to round. You'll notice we have a p here. That p stands for p-value, which we'll go into a little bit later, because that's an alternative way to test hypotheses. Let's take a look at one more example. Jamestown Steel Company manufactures and assembles desks and other office equipment at several plants in western New York State. The weekly production of the Model A325 desk at the Fredonia plant follows a normal distribution with a mean of 200 and a standard deviation of 16. Recently, because of market expansion, new production methods have been introduced and new employees hired. The VP of Manufacturing would like to investigate whether there's been a change in weekly production of this desk. In a sample of 50 weeks production, there was a mean of 203.5 desks produced. At the 0.01 significance level, is the mean number of desks produced at the Fredonia plant different from 200? So we have a rough idea what they're looking for. Now let's go back and list out what they've told us. We know that normally they had been producing 200 desks per week with a standard deviation of 16. They told us that in our sample of 50 weeks, so n equals 50, we found a mean of 203.5 desks produced. At a 0.01 significance level, so that means alpha equals 0.01, is the mean number of desks produced different from 200? They don't tell us anything about it being more than or less than. They're asking, has there been a change, basically? So different implies, has there been change? And this is our indicator of a two-tailed test. So what makes the two-tailed test a little bit different is instead of having everything isolated on one side, this alpha you have to split in half, and half of that goes to each side. So it means that this part is alpha over 2, which is 0.005, and this part is alpha over 2 as well. Now, the other part of that is you actually have two critical values now, and we'll get into those after we set up our null and alternative hypothesis. Since we've identified that this is two-tailed, there's only one setup that it could be. The mean is equal to 200, or the mean is not equal to 200. Now, using again the table or the calculator, whichever method you prefer, go ahead and find your critical values. So using inverse norm, we're looking for an area of 0.005 in the tail, which gives us a z-score of negative 2.576. If you use the table, you'll get roughly the same thing. And let's go into that just so we can see how this all works. 0.005, closest thing we can get. It's right between 2.57 and 2.58, so you would use 2.575 or the number that you found in the calculator, which is a little bit more accurate. Now, if our critical value on the left side is negative 2.575 or whatever you round it to, On the right side, because of the symmetry here, this has to be the positive version of that. And if you don't believe me, take a look at what you're finding here. What's the area to the left of 0.005? It's going to be everything is 0.995. So if you look up the closest thing to 0.995, you'll see again that we are right between positive 2.57 and positive 2.58. So same process. Once you have your critical value or values, go ahead and find your test statistic. Again, whether you do this by hand or in the calculator, it's up to you. Our z-test is equal to 203.5 minus 200 divided by 16 over the square root of 50. Again, the choice is yours if you want to type this in, or you can use your test function, still a z-test here. And this time we are testing this as a two-tailed test. So this time we found that we had a z-test statistic of about 1.547. Which again, if you treat this like a number line where 0 is in the center, this falls right around here. And because it's not in our tail region, in other words, it's not in the rejection region on either side, we have to say that we failed to reject the null hypothesis. So what does that imply about this data? That means that we do not have evidence supporting that there's been a change in the number of desk production, which if you were the person in charge of market expansion and you see that there's not been a significant change in production, what might that indicate? So this is the interpretation part. This is what's important. If you're trying to make more money, there's no indication that you're actually producing anything greater. Subsequently, that could affect your bottom line. Now, in terms of how this applies outside of a business perspective, you can use hypothesis testing to see if some type of drug test is even safe or something of that nature. So if you were using this to test a new medication on the market, you could essentially verify to see, is there too high a risk of something like a side effect or a deadly side effect? Anything like that. Hypothesis testing really is quite versatile. In the next video, we'll explore what happens in situations where sigma is unknown. See you there.